On Christmas Day 2021, humanity launched the most powerful telescope ever built into space. The James Webb Space Telescope, JWST, was a monument to human ambition, 30 years in the making, $10 billion in cost. A machine so precise that its 18 hexagonal mirrors had to be aligned to within nanometers across a structure the size of a tennis court. It was designed to peer deeper into space and therefore deeper into time than any instrument before it. It would see the first stars, the first galaxies, the cosmic dawn when light first broke through the darkness of the early universe. We expected discovery, we expected wonder, we expected to fill in the missing pieces of our cosmic story, to watch in unprecedented detail as the universe assembled itself from primordial gas into the grand structures we see today. What we didn't expect was a crisis. Within months of JWST beginning its observations, astronomers started seeing things that shouldn't exist. Galaxies appeared in the data, not just any galaxies, but massive, mature, fully formed galaxies, existing at times when such things should have been impossible. These weren't the small, scrappy, irregular proto-galaxies that our theories predicted for the early universe. These were monsters. Galaxies with hundreds of billions of stars. Galaxies with well-defined spiral arms. Galaxies that looked eerily similar to our own Milky Way, but existing when the universe was only a few 100 million years old. To put this in perspective, imagine you're watching a time-lapse of a tree growing from a seed. You expect to see the seed germinate, a small shoot emerge, a sapling grow gradually over years. But instead, when you look at the very first frame, mere days after planting, you see a towering oak, fully mature, with thick trunk and spreading branches. That's not how trees grow. That can't be how trees grow. But there it is, in the data, undeniable. 8 billion years old, JWST is detecting fully formed galaxies that existed when the universe was less than 300 million years old, roughly 2% of its current age. That's not enough time. Not according to the Lambda CDM model, our standard cosmological model, the framework that has successfully explained everything from the cosmic microwave background to the large-scale structure of the universe. That model tells us how galaxies form. Slowly, through the gradual accumulation of matter drawn together by gravity, through the hierarchical assembly of smaller structures merging into larger ones. It's a bottom-up process that takes time, lots of time, but these early galaxies don't look like they had time. They look like someone skipped ahead in the cosmic movie, like the universe was in a hurry, like the first few 100 million years were far more eventful, far more productive than we ever imagined. Some of these galaxies are so massive, so luminous, so evolved, that their existence seems to violate basic principles of physics. To form a galaxy with 1 trillion solar masses worth of stars in only 300 million years would require star formation rates vastly higher than anything we've ever observed. It would require almost all the matter in a given region to convert into stars with impossible efficiency. It would require the universe to work differently in its youth than it does today. And it's not just one or two anomalies. As JWST's observations accumulated through 2022, 2023, and into 2024, the tension only grew. The telescope kept finding these impossible galaxies, kept pushing the boundaries of when and how structure could form. Papers appeared with titles like A Population of Red Candidate, Massive Galaxies 600 Myer After the Big Bang, and Panic. The panic was real, because if these observations are correct, if these galaxies really are as massive and as early as they appear, then something is wrong with our understanding of the universe. Either our model of galaxy formation is incomplete, or our measurements of cosmic age are off, or there's some new physics at work that we don't understand. The foundation of modern cosmology, a framework built over a century of observations and theory, was suddenly looking shaky. But here's what makes this story so fascinating. This isn't the first time the universe has surprised us. The history of cosmology is a history of shattered expectations, of observations that forced us to revise our most fundamental assumptions. The universe has repeatedly turned out to be stranger, more complex, more interesting than we imagined. Perhaps JWST is simply continuing that tradition, revealing yet another layer of cosmic complexity that our theories haven't yet captured. Or perhaps it's revealing something deeper, something that will require us to rethink not just how galaxies form, but the nature of the Big Bang itself, the properties of dark matter, or even the laws of physics in the early universe. In this script, we're going to explore what JWST found, why it's so troubling, and what it might mean for our understanding of the cosmos. We'll journey through the history of how we came to understand the early universe, from the first observations of distant galaxies to the construction of the standard cosmological model. We'll dive deep into the data JWST has collected and the contradictions it presents. We'll explore the possible explanations, from mundane measurement errors to exotic new physics, and we'll grapple with what it means when our most powerful telescope reveals a universe that doesn't quite match our expectations. This is the story of how humanity built a $10 billion machine to confirm what we thought we knew about the universe, and instead found ourselves confronting cosmic mysteries we hadn't anticipated. It's a story about the tension between theory and observation, about the courage required to question deeply held beliefs, and about the fundamental truth that the universe doesn't care about our models. It simply is, in all its strange and wonderful complexity. The James Webb Space Telescope was supposed to be a triumph, the culmination of decades of planning and the answer to our deepest questions about the cosmic dawn. Instead, it became a mirror reflecting back at us the limits of our understanding and the vast depths of what we still don't know. The universe's childhood, it turns out, was far more interesting than we imagined, and we're only beginning to understand just how interesting it really was. To understand why JWST's observations are so shocking, we need to understand what we thought we knew about the early universe. And to understand that, we need to go back to the beginning, not the beginning of the universe, but the beginning of our understanding of it. For most of human history, the cosmos was thought to be eternal and unchanging. The stars were fixed in their celestial spheres, the heavens perfect and immutable. Even when Galileo pointed his telescope skyward in 1609 and saw moons orbiting Jupiter, mountains on the moon, and countless stars invisible to the naked eye, the fundamental assumption remained. The universe was static, infinite in time, unchanging in its essential nature. This assumption began to crack in the 1920s with Edwin Hubble's observations. We discussed Hubble in the context of vacuum decay, but his discovery deserves to be told again because it's the foundation of everything that follows. Hubble, working at the Mount Wilson Observatory with the largest telescope in the world, was measuring the spectra of distant galaxies. He found that their light was redshifted, stretched to longer wavelengths, shifted toward the red end of the spectrum. This redshift had a simple interpretation. The galaxies were moving away from us, and not just a few of them, but all of them. Every galaxy Hubble observed was receding. Moreover, the farther away a galaxy was, the faster it was receding. This relationship, velocity proportional to distance, could only mean one thing. Space itself was expanding, carrying the galaxies along with it like raisins in rising bread dough. If space is expanding now, then it was denser in the past. Run the expansion backward in time, and everything gets closer together, hotter, denser. Eventually you reach a point where the universe was so hot and dense that atoms couldn't exist, where matter was a plasma of electrons and nuclei. Go back further, and even atomic nuclei break apart into their constituent protons and neutrons. Further still, and even protons and neutrons dissolve into a soup of quarks and gluons. This backward extrapolation led to an inescapable conclusion. The universe had a beginning. There was a moment when everything we can observe, all the matter, all the energy, all of space itself, emerged from an incredibly hot, dense state. The name stuck, despite the misleading imagery it evokes. The Big Bang wasn't an explosion in space. It was the expansion of space itself, everywhere at once, from a state of extreme density and temperature. But for decades, this remained a theoretical framework without detailed observational support. Yes, the universe was expanding, but what did the early universe actually look like? How did it evolve from that initial hot, dense state to the cosmos we see today? The breakthrough came in 1964, quite by accident. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs, were trying to calibrate a radio antenna for satellite communications. They kept detecting a persistent background noise, a radio hiss that came equally from all directions in the sky. They cleaned the antenna, removed pigeon droppings, checked every component. The noise remained. What they discovered was the afterglow of the Big Bang itself, the cosmic microwave background radiation, or CMB. In the early universe, When everything was hot enough to be a plasma, photons couldn't travel freely. They constantly scattered off the charged particles. But about 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the universe became transparent to light. The photons that had been trapped in the plasma were released, streaming freely through space. Those photons have been traveling ever since, but the expansion of the universe has stretched their wavelengths from visible light to microwaves. 8 billion years. Light that comes from every direction because it was emitted everywhere at once when the universe became transparent. The discovery of the CMB was profound. It confirmed the Big Bang model and gave us a snapshot of what the universe looked like at age 380,000 years. And that snapshot revealed something remarkable. The universe at that time was extraordinarily smooth, extraordinarily uniform. The temperature variations in the CMB, which correspond to density variations in the matter, are tiny, only about 1 part in 100,000. Some regions were slightly denser, slightly hotter. Others were slightly less dense, slightly cooler. But overall, the universe was remarkably homogeneous. This smoothness presented a puzzle. Today's universe is anything but smooth. Matter is clumped into galaxies. Galaxies are grouped into clusters. Clusters form superclusters and filaments. Vast cosmic webs of structure with equally vast voids between them. How did we get from the smooth universe of the CMB to the lumpy universe we see today? The answer is gravity. Those tiny density fluctuations in the early universe, regions that were slightly denser than average, had slightly stronger gravity. They attracted more matter, becoming denser still, which increased their gravity further. This runaway process, called gravitational instability, gradually amplified the small fluctuations into larger and larger structures. But there's a catch. This process is slow. Gravity is the weakest of the fundamental forces, and building up structure through gravitational attraction takes time. You can calculate how long it should take for a region that's 1 part in 100,000 denser than its surroundings to collapse into a bound object. The answer is hundreds of millions to billions of years. Moreover, the process is hierarchical. Small structures form first, then merge to form larger structures, which merge to form even larger structures. The first bound objects would be relatively small, perhaps millions of solar masses. These would merge over time into larger halos, which would merge into galaxy-sized structures, which would eventually merge into galaxy clusters. It's a bottom-up process, a gradual accumulation of mass through mergers and accretion. This hierarchical model of structure formation became the foundation of modern cosmology in the latter half of the 20th century. It was refined and elaborated as observations accumulated and computer simulations became more sophisticated. By the 1990s, cosmologists had developed what's called the lambda CDM model. Lambda for dark energy, that mysterious force accelerating the universe's expansion. CDM for cold dark matter, the invisible matter that provides most of the universe's gravitational pull. The lambda CDM model is remarkably successful. It explains the CMB in exquisite detail, not just its temperature, but the pattern of hot and cold spots across the sky, which encodes information about the universe's composition and geometry. It explains the large-scale distribution of galaxies. It explains the abundances of light elements produced in the first few minutes after the Big Bang. It predicts the acceleration of the universe's expansion, which was observationally confirmed in 1998. It's been tested against countless observations and passed every test. Within this framework, cosmologists built a detailed timeline of galaxy formation. Ordinary matter, hydrogen and helium gas, would fall into these halos, heat up from compression, and eventually cool and condense. When enough gas accumulated, it would become dense enough for gravity to ignite nuclear fusion. Stars would be born. The first stars, formed from pristine hydrogen and helium with no heavier elements, would be massive, hot, and short-lived. These population 3 stars have never been directly observed, but theory suggests they would burn through their fuel in just a few million years before exploding as supernovae. These explosions would enrich the surrounding gas with heavy elements: carbon, oxygen, iron, all the elements forged in stellar cores, enabling the formation of a second generation of stars more similar to those we see today. Over time, more and more gas would accumulate in dark matter halos, more stars would form, and these stellar collections would begin to resemble galaxies. But early galaxies should be small, Irregular, actively forming stars. Nothing like the grand spiral galaxies we see in the nearby universe. Those mature structures would take billions of years to assemble through mergers and accretion. This was the picture cosmologists had refined over decades of theoretical work and observational testing. And crucially, it made clear predictions about what the early universe should look like. At redshift Z+10, corresponding to about 480 million years after the Big Bang, we should see small, low-mass galaxies, perhaps 10 million to a billion solar masses, actively forming stars. At Z+15, about 270 million years after the Big Bang, we'd expect even smaller, more primitive structures. At ZD20 and beyond, we're in the realm of the very first galaxies. Tiny, faint, difficult to detect, but definitely not massive or mature. This is where Hubble Space Telescope came in. Launched in 1990 and repeatedly serviced by astronauts over its 3 decades of operation, Hubble revolutionized our view of the universe. One of its primary missions was to observe the most distant, earliest galaxies it could reach. Through deep observations like the Hubble Ultra Deep Field, images where Hubble stared at a tiny patch of sky for hundreds of hours, accumulating photons from the faintest, most distant objects, astronomers could see galaxies as they appeared billions of years ago. And what Hubble found largely confirmed the lambda CDM predictions. Distant galaxies were indeed smaller, bluer, indicating active star formation, more irregular, and less massive than nearby galaxies. There was a clear evolution. The universe's galaxies had grown over time through mergers and star formation, exactly as the hierarchical model predicted. By looking at galaxies at different distances, and therefore different times in cosmic history, astronomers could reconstruct the galaxy formation process in impressive detail. But Hubble had limits. It primarily observed in visible and near-infrared wavelengths. For the most distant galaxies, the expansion of the universe stretches their light so much that visible light is redshifted all the way into the infrared. To see the earliest galaxies, those existing in the first few 100 million years, you need a telescope optimized for infrared observations. You need a much larger mirror to collect more light from these faint, distant sources. And you need to be in space above Earth's atmosphere, which absorbs much of the infrared spectrum. You need the James Webb Space Telescope. JWST is a marvel of engineering. 4 meters, giving it more than 6 times the light collecting area. 6 to 28 micrometers. Its mirrors are coated with gold, which reflects infrared light with high efficiency. And it operates at the second Lagrange point, L2, a gravitationally stable location about 1 million miles from Earth, where a massive sun shield keeps the telescope in perpetual shadow, cooling it to just above absolute zero, necessary for detecting faint infrared signals without being swamped by the telescope's own thermal radiation. The telescope took 30 years to develop. Thousands of engineers and scientists worked on it. The complexity was staggering. The mirrors had to unfold in space like cosmic origami, then be aligned to nanometer precision. The sun shield, the size of a tennis court, had to deploy perfectly. Hundreds of mechanisms had to work flawlessly with no possibility of repair by astronauts as Hubble had enjoyed. When JWST launched on Christmas Day 2021, the tension in the astronomical community was palpable. If anything went wrong during deployment, the mission would fail. Decades of work, billions of dollars, the hopes of an entire field, all riding on a 6-month deployment sequence. It worked. Mechanism by mechanism, the telescope unfolded, the mirrors aligned, the instruments cooled to operating temperature. By July 2022, JWST released its first science images, and they were breathtaking. Galaxies rendered in unprecedented detail, nebula glowing with structure invisible to Hubble, the deepest, sharpest infrared view of the cosmos ever obtained. And immediately, within those first images, astronomers saw hints of something unexpected. Galaxies that appeared to be at very high redshifts, meaning very early times, but were brighter and more structured than anticipated. At first, there was caution. These were preliminary observations, and distance measurements based on color can be unreliable. Spectroscopic confirmation, actually measuring the spectrum of the galaxy to determine its redshift precisely, would be needed. But as more observations came in, as spectroscopy confirmed the high redshifts, the pattern became undeniable. JWST was seeing massive galaxies at Z8, Z10, ZT12, even candidates at ZU16 and beyond, galaxies that, according to the Lambda CDM model and our understanding of hierarchical structure formation, shouldn't exist yet. The universe's childhood, it seemed, was far more precocious than we'd imagined. Let's talk about what JWST actually found, starting with some specific examples that captured the attention and concern of the astronomical community. The authors reported finding several galaxies at redshifts around ZSU7 to ZSR9, corresponding to times when the universe was 600 to 800 million years old. These weren't just any galaxies. Their stellar masses were estimated to be between 10 and 100 billion times the mass of the Sun, comparable to our Milky Way. This was shocking. To assemble 100 billion solar masses worth of stars in only 600 million years requires extraordinary star formation rates. Let's do the math. If you start with a pristine gas cloud and want to convert it into 100 billion solar masses of stars in 600 million years, you need to form stars at an average rate of about 170 solar masses per year. For comparison, the Milky Way currently forms stars at a rate of about 1 to 2 solar masses per year. Even accounting for the fact that the early universe had more available gas and higher star formation rates, this seemed impossibly high. Moreover, there's an efficiency problem. Not all the gas in a region can turn into stars. Much of it is ejected by supernovae, stellar winds, and other feedback processes. The star formation efficiency, the fraction of available gas that actually becomes stars, is typically around 10 to 20% in observed galaxies. To form 100 billion solar masses of stars with that efficiency, you'd need to start with 500 billion solar masses of gas in the region, which is a huge amount of matter to have concentrated in one place so early. The authors of the paper were careful to note uncertainties. Distance measurements based on photometry, measuring the brightness in different wavelength bands, can be unreliable. A dusty galaxy at lower redshift might mimic the colors of a very distant galaxy. Stellar mass estimates depend on assumptions about the star formation history and the distribution of stellar ages, which are uncertain. But even accounting for these uncertainties, the galaxies appeared problematic for standard models. As JWST continued observing through late 2022 and into 2023, more examples accumulated. A paper announced the discovery of galaxies at ZPI 910, appearing as they were 500 to 550 million years after the Big Bang, with stellar masses of 10 to 20 billion solar masses. Another paper reported a galaxy at ZTARB 11, 470 million years after the Big Bang, with a stellar mass possibly exceeding 40 billion solar masses. Yet another study found galaxies at ZEBA 1213 that appeared to have already assembled into rotating disk structures, with clear signs of organized motion, the kind of dynamical maturity that should take much longer to develop. 8 and other candidates pushed even earlier, to Z16 and beyond, corresponding to just 250 million years, or less, after the Big Bang. If these distance estimates are correct, and spectroscopic follow-up has confirmed at least some of them, we're seeing substantial galaxies at times when the Lambda CDM model predicts only the tiniest protogalactic structures should exist. Let me emphasize this point by returning to our tree analogy. According to the standard timeline, structure formation begins from tiny seeds, the quantum fluctuations imprinted in the CMB. These seeds grow slowly through gravity. At 100 million years, you'd expect small dark matter halos with perhaps the first stars forming inside them. At 200 million years, you might have small stellar clusters, the precursors to galaxies. At 300 to 400 million years, you'd have small, low-mass galaxies starting to take shape. Only after billions of years would you expect to see massive, mature galaxies like our Milky Way. But JWST is showing us massive galaxies, not Milky Way-sized in some cases, but comparable in mass, existing at 500 to 600 million years, and galaxy candidates existing even earlier. It's like seeing an acorn planted last week that's already a towering oak tree. Now let's be careful here. Not all the claims have held up under scrutiny. Some of the initial reports of extremely distant, extremely massive galaxies turned out to be less extreme upon further analysis. When you measure a galaxy's distance photometrically, you're essentially looking at its colors, how bright it is in different wavelength bands, and using that to estimate its redshift. But this can be fooled by various effects. A dusty galaxy at lower redshift can appear very red, mimicking the signature of an extremely distant galaxy. Certain types of active galactic nuclei can have unusual colors that get mistaken for high redshift. Spectroscopy, actually breaking the galaxy's light into its spectrum, and measuring the precise wavelengths of emission lines from elements like hydrogen and oxygen, gives much more reliable distances. As spectroscopic follow-up observations have been performed on many of the initial candidates, some have turned out to be closer than initially estimated. That Z516 candidate might actually be at Z5. That apparently massive galaxy might be at lower redshift and less massive. This is the scientific process working as it should. Initial claims based on preliminary data are tested and refined with more detailed observations. But here's the crucial point. Even after this winnowing process, even after the most extreme claims have been walked back, a tension remains. There are still spectroscopically confirmed galaxies at Z10, Z11, Z13 that are more massive and more mature than standard models comfortably predict. The number density of bright galaxies at high redshift, how many such galaxies exist per unit volume of space, is higher than lambda CDM simulations predict. The stellar masses, assembled by redshift Z8, appear to exceed what the models can produce without invoking extreme star formation efficiencies. Several independent research groups have quantified this tension. One analysis compared JWST observations to predictions from large cosmological simulations that follow the evolution of dark matter and gas from the early universe to the present, tracking how structures form and merge over cosmic time. These simulations are based on lambda CDM and have been carefully calibrated against observations of the local universe. When extended to high redshifts, they make clear predictions about the abundance and properties of early galaxies. The JWST observations exceed these predictions. By redshift Z10, JWST is finding galaxies that are too abundant. There are simply more bright, massive galaxies than the simulations produce. By redshift Z13, the discrepancy is even larger. Some studies estimate that the observed number density of bright galaxies at Z10 is an order of magnitude higher than predicted. An order of magnitude, 10 times more galaxies than there should be. This can't be easily explained away by observational uncertainties. Yes, there are error bars on the measurements, but they're not large enough to close a factor of 10 gap. And the tension appears across multiple independent studies using different methods and different data sets. Another way to quantify the problem is through stellar mass density. If you add up all the stellar mass in galaxies out to a certain redshift, you get the stellar mass density at that epoch. How much of the universe's matter has been converted into stars by that time? Lambda CDM makes predictions about how stellar mass density should grow with time. It starts near zero in the first 100 million years. There are no stars yet. Then gradually increases as more and more gas is converted into stars in galaxies. JWST observations suggest that stellar mass density at Z10 is higher, perhaps significantly higher, than standard models predict. Again, the discrepancy is difficult to reconcile with observational uncertainties alone. It appears that the early universe was more efficient at forming stars, or had more time to form stars, or operated under different conditions than our models assume. There's another peculiar feature in the JWST data. The galaxies aren't just massive, they're mature. Some of them show evidence of already containing old stellar populations, stars that formed even earlier and have been aging for hundreds of millions of years. Remember, a massive star lives only a few million years. But lower mass stars, like our Sun, live for billions of years. If you observe a galaxy and detect the light from low mass stars, that tells you those stars have been around for a while. The galaxy isn't brand new, it has history. Some of the JWST galaxies at ZC8 to Z10 and show evidence of stellar populations that are already hundreds of millions of years old. This pushes back the formation time even earlier. If a galaxy at Z10, 4 to 80 million years after the Big Bang, contains stars that are 300 million years old, those stars must have formed at Z15 or so, 250 million years after the Big Bang. We're being forced to conclude that significant star formation was happening even earlier than the galaxies JWST is directly detecting. And then there's the morphology, the shapes and structures of these early galaxies. Hubble observations of high redshift galaxies typically showed irregular, clumpy, chaotic structures. This made sense. These are galaxies in the process of forming, violently assembling through mergers and gas accretion, not yet settled into the organized structures we see in mature galaxies today. Spiral arms, well-defined disks, central bulges, these features take time to develop. But some JWST observations show surprisingly organized structures at high redshift. Galaxies with disk-like morphologies, with evidence of rotation, with hints of spiral structure, existing at Zeba 10 and beyond. This suggests that galaxies reach dynamical maturity faster than expected, that the processes of settling, disk formation, and structural organization operated more efficiently in the early universe. One particularly striking example is a galaxy with a clear disk structure at Z06, corresponding to about 900 million years after the Big Bang. Detailed analysis of its velocity field, how different parts of the galaxy are moving, shows evidence of ordered rotation, like a spiral galaxy in the present-day universe. The galaxy appears to be dynamically mature, settled, organized. According to models, disks form when gas falls into a galaxy and settles into a rotating structure, spinning up due to conservation of angular momentum. This process should take substantial time, multiple orbital periods, which at these distances can be hundreds of millions of years. Yet here's a well-formed disk existing when the universe is less than 1 billion years old. Now let's address a critical question. Could all of this be a mistake? Could there be systematic errors in the observations or analysis that explain away the tension? Astronomers have considered many possibilities. Perhaps dust is affecting the observations, making galaxies appear more massive than they really are. Dust absorbs starlight and re-emits it in the infrared, which could affect mass estimates. But detailed modeling suggests dust alone can't explain the observed properties. Moreover, some of the high redshift galaxies appear relatively dust-free based on their spectral properties, yet still appear massive. Perhaps active galactic nuclei, supermassive black holes actively feeding on gas and emitting enormous amounts of light, are contaminating the measurements, making galaxies appear brighter and more massive than they are. This is possible in some cases, but spectroscopic observations can usually identify AGN through their characteristic emission lines, and many of the problematic galaxies don't show clear AGN signatures. Perhaps the stellar mass estimates are systematically wrong? Perhaps we're misunderstanding how to convert observed light into estimated stellar mass. This depends on assumptions about the stellar population, the distribution of stellar masses, ages, and metallicities. If those assumptions are wrong, the mass estimates could be off. But you'd need the masses to be overestimated by factors of 10 or more in some cases, which would require very unusual stellar populations, quite different from anything observed in the nearby universe. Perhaps the redshifts themselves are wrong? Perhaps galaxies we think are at Z1 are actually at Z5 or Z3, closer and less problematic. This is why spectroscopic confirmation is crucial. And as mentioned, many of the galaxies have now been spectroscopically confirmed to be at the high redshifts initially estimated. The most extreme claims haven't all held up, but enough have been confirmed to maintain the tension. The consensus emerging in the astronomical community is that the observations are largely correct. JWST really is detecting an excess of massive, mature galaxies at high redshift. The tension with lambda CDM is real. The question is, what does it mean? This brings us to the realm of interpretation and speculation. Because if the observations are correct, then either our understanding of galaxy formation is incomplete, or our cosmological model needs adjustment, or something about the early universe was different than we've assumed. The universe has given us a puzzle. The data from the most advanced telescope ever built is telling us a story that doesn't quite fit the narrative we've constructed, and now we must figure out what that means. When observations contradict theory, scientists face a choice. The theory might be wrong, requiring fundamental revision, or the theory might be incomplete, missing key physical processes that become important in the regime being tested, or the observations might be misleading, affected by systematic errors or selection effects not properly accounted for. In the case of JWST's early galaxy observations, all three possibilities remain on the table, and the astronomical community is actively exploring each one. Let's walk through the leading explanations, from the most conservative to the most radical. Explanation 1. We've underestimated star formation efficiency. The simplest explanation is that early galaxies were just really good at forming stars. In the present-day universe, star formation is inefficient. Most of the gas in a galaxy never becomes stars. It's either too hot, or it's expelled by supernova feedback, or it never cools and condenses sufficiently. The star formation efficiency, the fraction of available gas that actually turns into stars, is typically 10–20%. But perhaps in the early universe, conditions were different. The gas was more pristine, without the heavy elements that can inhibit star formation. The gas was denser, making it easier to cool and collapse. Dark matter halos were growing rapidly through accretion, constantly funneling fresh gas into galaxies. Perhaps under these conditions, star formation efficiency could be much higher, 50%, 70%, maybe even approaching 90% in some regions. If early galaxies could convert most of their available gas into stars, rather than just a fraction, then the massive galaxies JWST observes become more plausible. You could assemble 100 billion solar masses of stars in 600 million years if almost all the gas in the region becomes stars. This explanation has the virtue of requiring only modest changes to our understanding. The lambda CDM cosmological model remains intact. We're not changing fundamental physics, just adjusting our understanding of astrophysical processes, how gas cools, fragments, and turns into stars, in the unique conditions of the very early universe. The problem is that there are physical limits to star formation efficiency. Supernovae inject energy into the surrounding gas, heating it and pushing it outward, suppressing further star formation. This feedback process is well studied and seems unavoidable. When massive stars explode, they blast gas out of galaxies, particularly in the low-mass systems characteristic of the early universe, which have weaker gravity and can't hold on to their gas as effectively. To achieve the required star formation rates while overcoming feedback, you'd need very specific conditions, and it's not clear those conditions are physically plausible. Moreover, extremely high star formation rates should produce observable signatures. Massive stars emit ultraviolet radiation that ionizes surrounding gas, creating emission lines in the galaxy's spectrum. Supernovae enrich the gas with heavy elements, changing its chemical composition. If early galaxies were forming stars at the extreme rates required, we should see evidence in their spectra, and in some cases we do, but not always at the levels you'd expect from such extreme star formation. So while increased star formation efficiency might be part of the answer, it's unclear if it can fully resolve the tension without requiring conditions that seem physically implausible or contradicting other observations. Explanation 2. The initial mass function was different. Stars don't all have the same mass. When a cloud of gas fragments and collapses to form stars, you get a distribution of stellar masses, a few very massive stars, many more medium mass stars, and huge numbers of low mass stars. This distribution is called the initial mass function, or IMF. In the nearby universe, the IMF appears to be remarkably universal. Regardless of whether you look at star-forming regions in our galaxy or in distant galaxies, the distribution of stellar masses follows the same pattern, called the Salpeter IMF, or the more refined Krupa-Chabrier IMF. Most stars that form are low mass, red dwarfs less than half the Sun's mass, with progressively fewer stars at higher masses. But perhaps in the early universe, the IMF was different. Perhaps the first generations of stars were systematically more massive, what's called a top-heavy IMF. If early galaxies formed preferentially massive stars, this could help explain the JWST observations in several ways. First, massive stars are much more luminous than low-mass stars. A single star, 100 times the mass of the Sun, can be 1,000,000 times more luminous. If early galaxies formed proportionally more massive stars, they'd be brighter for a given stellar mass, which could partly explain why JWST sees such bright galaxies. Second, massive stars live fast and die young. A 100 solar mass star lives only a few million years before exploding as a supernova. If you form a burst of massive stars, you get a brief period of enormous luminosity, but then those stars die off, leaving behind compact remnants, neutron stars or black holes, that contribute mass but little light. When we observe a galaxy and estimate its stellar mass based on its luminosity, we're assuming a standard IMF. If the IMF was top-heavy, we might be overestimating the stellar mass. because much of the mass is in dead remnants that don't contribute to the light. Wait, that seems backward. If we're overestimating stellar mass, that would reduce the tension, not increase it. But there's another effect. If early galaxies had top-heavy IMFs, they could have assembled their stellar mass more quickly in a brief, intense burst, then dimmed as the massive stars died off. The galaxies JWST sees might be catching these systems during their peak brightness. The problem with invoking a different IMF is that there's limited direct evidence for it. The theoretical reasons for expecting a top-heavy IMF in the early universe are somewhat speculative, based on the idea that metal-free gas might cool less efficiently and therefore fragment into larger clumps. But detailed simulations of primordial star formation give varied results, and it's unclear how much the IMF would differ from the present day. Moreover, if the IMF was radically different, it would affect other observables. A top-heavy IMF produces more supernovae, more heavy elements, more high-energy radiation. These should leave signatures in the properties of the galaxies and in the intergalactic medium. Some observations hint at possible IMF variations, but the evidence isn't conclusive, so again, this might be part of the answer, but it's unclear if it resolves the full tension. Explanation 3. Dark matter behaves differently than we thought. Lambda CDM assumes that dark matter is cold, meaning the dark matter particles move slowly compared to the speed of light. Cold dark matter clumps efficiently under gravity, forming the halos that seed galaxy formation. The clumping process is hierarchical. Small halos form first, then merge into larger halos over time. But what if dark matter isn't entirely cold? What if it's warm or has some small-scale suppression of structure? Warm dark matter particles move faster, which tends to smooth out structures on small scales while preserving large-scale structure. If dark matter is slightly warmer than the standard cold dark matter, it could suppress the formation of the smallest dark matter halos, while still allowing larger structures to form. This might seem counterintuitive. How does suppressing small-scale structure help explain the observed abundance of early galaxies? The idea is that if small halos don't form efficiently, more of the matter ends up in larger halos. Instead of hierarchical bottom-up assembly where countless tiny halos slowly merge into larger ones, you'd have a more top-down process where larger structures form more directly. This could potentially accelerate galaxy formation, allowing substantial masses to assemble earlier than in the standard cold dark matter scenario. It's a speculative idea, and it faces challenges. Warm dark matter changes predictions for the small-scale distribution of galaxies in the present day, and those predictions need to match observations, which constrain how warm dark matter can be. Alternatively, dark matter might interact with itself, or with normal matter, in ways not included in the standard model. These interactions could affect how dark matter clumps, potentially changing the timeline of structure formation. But again, these ideas are speculative and need to be consistent with many other observations of dark matter's behavior. Explanation 4. Something is wrong with our distance measurements. Perhaps the most conservative explanation is that we're systematically mismeasuring distances. If galaxies we think are at Z210 are actually at Z27, the tension largely disappears. An extra few hundred million years makes a big difference for how much mass can plausibly assemble. But as I've mentioned, spectroscopic confirmation has verified many of the high redshifts. When you measure the spectrum of a galaxy, you're measuring the precise wavelengths of emission lines from elements like hydrogen, oxygen, and neon. These lines have characteristic wavelengths determined by atomic physics. By measuring how much those wavelengths are stretched, the redshift, you can determine the galaxy's distance very precisely. Spectroscopy doesn't have the ambiguities of photometric distance estimates. Could spectroscopy itself be fooled? It's hard to see how, unless there's some systematic calibration error affecting all the observations, which seems unlikely given the care taken in data processing and the consistency of results across different instruments and programs. So while measurement error is always a possibility in science, it seems increasingly unlikely that this explains the full extent of the tension. Explanation 5. The cosmological model is wrong. Now we venture into more radical territory. What if the lambda CDM model itself needs revision? What if our understanding of the universe's expansion history, or its age, or the timeline of structure formation is somehow off? One possibility that's received attention is that the Hubble constant, the rate of the universe's expansion, might be different than the value inferred from the CMB. There's already a Hubble tension in cosmology. Measurements of the Hubble constant using nearby supernovae give a value about 10% higher than the value inferred from the CMB, 5 or 12 billion years old. A younger universe makes the JWST observations even more problematic, not less. If the universe at ZU10 was only 350 million years old instead of 480 million years old, that's even less time for galaxies to form. So this goes in the wrong direction. Unless, and this is where it gets speculative, the Hubble tension points to new physics in the early universe, some period of different expansion or different physical conditions that gave structure more time to form than the standard timeline suggests. Some physicists have proposed exotic scenarios involving early dark energy or modifications to general relativity that change the early expansion history in ways that could help with structure formation. These ideas are highly speculative and face significant challenges. They need to explain not just the JWST observations, but all the other observations that lambda CDM successfully accounts for: the CMB, the abundance of light elements, the large-scale structure of galaxies, the acceleration of the expansion. Changing one aspect of the model tends to break its predictions for other observations, so finding a modification that helps with early galaxy formation without contradicting everything else is difficult. Another radical possibility: what if the universe underwent a period of early structure formation that predates the standard timeline? Some very exotic models propose that structures could form before recombination, the epoch when the CMB was emitted, or that there was a pre-Big Bang phase that seeded structures, or other non-standard scenarios. These ideas are at the speculative fringe, and most cosmologists are hesitant to abandon a model as successful as lambda CDM without overwhelming evidence. But if the tension with JWST observations persists and grows, more radical solutions might need to be considered. Explanation 6. The universe had a lucky draw. There's one more possibility, perhaps the most philosophically interesting. Maybe we're just lucky, or unlucky, depending on your perspective. The observed universe, the region of space we can see, is finite, with a radius of about 46 billion light years. But the actual universe could be vastly larger, perhaps infinite. If it's infinite, then every possible configuration of matter that's consistent with the laws of physics exists somewhere. In an infinite universe, most regions would have structure formation proceed normally, following the lambda CDM predictions. But a small fraction of regions would have statistical fluctuations, rare arrangements of density fluctuations in the early universe that happen to allow faster structure formation. By chance, these regions might have had an unusually high density of peaks in the matter distribution, or particularly favorable configurations for rapid collapse, or other statistical accidents that accelerated galaxy formation. If we happen to live in one of these rare regions, we'd see an excess of early massive galaxies compared to the average across the universe. We'd be in a cosmic outlier, a statistically unusual bubble where things happened faster than typical. This explanation is unsatisfying because it invokes luck rather than new physics. It also raises questions about why we'd find ourselves in such an unusual region, though anthropic reasoning might provide an answer. If galaxies forming earlier affects the conditions for life, perhaps observers are more likely to find themselves in regions where early galaxy formation was enhanced. But without independent evidence that we're in an unusual region, this explanation feels like giving up on finding a deeper understanding. Where does this leave us? The honest answer is uncertain. The astronomical community is still grappling with JWST's observations, still working to understand whether they represent a crisis for cosmology or a puzzle that can be solved within the existing framework. What's clear is that the early universe was more complex, more active, more interesting than the simplest models predicted. Whether that requires abandoning lambda CDM or just refining our understanding of astrophysical processes remains to be seen. More observations will help. JWST is continuing to survey the high redshift universe, building up larger samples of early galaxies and measuring their properties in greater detail. Spectroscopic follow-up will confirm or refute the most extreme distance claims. Detailed studies of stellar populations, morphologies, and dynamics will constrain how these galaxies formed and evolved. Ground-based telescopes are also contributing. The next generation of extremely large telescopes, with mirrors 30 to 40 meters in diameter, will provide complementary observations. particularly spectroscopy of faint high redshift galaxies. Radio observations with ALMA and future facilities will probe the gas content and dynamics of early galaxies. And theorists are working hard to refine models, exploring the range of possible star formation histories, IMFs, feedback mechanisms, and other astrophysical processes that might explain the observations within the Lambda CDM framework. Simulations are being improved with higher resolution and more sophisticated physics to see if they can reproduce what JWST sees. Within a few years, the picture should become clearer. Either the tension will dissolve as we understand the observations better and refine our models, or it will persist and deepen, forcing us to seriously consider more radical explanations. What JWST has done is remind us that the universe is under no obligation to match our expectations. We built our cosmological model from observations of the local universe, of the CMB, of the distribution of nearby galaxies. We've extrapolated that model backward in time, using theory and simulations to predict what the early universe should look like. And now we're testing those predictions with the most powerful observatory ever built. The universe is giving us answers. They're just not quite the answers we expected. There's a famous quote, often attributed to Arthur C. JWST's observations of the early universe feel like a confirmation of that sentiment. We launched a $10 billion telescope, expecting to fill in details, to see the first stars and first galaxies, to watch the cosmic dawn unfold according to the script we'd written based on decades of theoretical work and observational testing. Instead, we found a universe that seems to have ignored parts of the script, that did things faster and more efficiently than our models predicted, that challenges us to revise our understanding. This is both humbling and exciting. Humbling because it reveals the limits of our knowledge, the gap between our theories and reality. Exciting because it means there's still so much to discover, so much we don't understand about how the universe works. The history of cosmology is a history of surprises. When Hubble discovered the universe was expanding, it overturned the assumption of a static cosmos that had held for millennia. When Penzias and Wilson detected the cosmic microwave background, it confirmed that the universe had a hot, dense beginning. When observations revealed that the universe's expansion was accelerating, it meant that some mysterious dark energy permeates all of space. Each discovery forced a revision of our cosmic story. Each one revealed that the universe was stranger than we'd imagined. JWST's observations of massive galaxies in the early universe might be the next chapter in this story. Whether they force a fundamental revision of Lambda CDM or can be accommodated within the existing framework remains to be seen. But either way, they're teaching us something important about the cosmos. If the observations can be explained within Lambda CDM through improved understanding of star formation, feedback, and other astrophysical processes, then we're learning that the early universe was a more violent, more efficient, more dynamic place than we appreciated. The first few 100 million years were a crucial epoch when much of the mass that would eventually form galaxies was already being assembled into stars. The cosmic dawn wasn't a gradual brightening, but a sudden ignition, a period of furious activity that shaped the universe we see today. If the observations require modifications to dark matter, to the expansion history, to the cosmological model itself, then we're on the cusp of a revolution in our understanding. We'd be learning that the fundamental picture we've built over the past century is incomplete, that new physics is needed to explain how the universe evolved from its primordial state to its present complexity. Either way, we're learning. That's what science does. It confronts theory with observation, refines understanding through data, follows the evidence wherever it leads, even when it challenges cherished beliefs. And there's something beautiful in that process. We're not just passively receiving knowledge from the universe, we're actively interrogating it, building instruments to probe its deepest secrets, using mathematics and physics to decode the messages written in starlight. The fact that a species of primates on a small planet orbiting an ordinary star can build a machine capable of seeing galaxies as they appeared 13 billion years ago, can calculate the conditions in the early universe, can test those calculations against observations. That's extraordinary. We're doing what humans have always done, telling stories about the cosmos, trying to understand our place in it, seeking to comprehend the nature of existence itself. But now our stories are constrained by data, tested by observation, refined through the rigorous process of science. They're not just stories, they're models, frameworks that make predictions and can be proven wrong. And being proven wrong is part of the process. It's not a failure, it's how we learn. Every time the universe surprises us, every time observations conflict with predictions, we're given an opportunity to improve our understanding, to build better models, to glimpse new aspects of cosmic truth. JWST's observations of the early universe are a gift in that sense. Yes, they create problems for our models. Yes, they force us to question assumptions we'd grown comfortable with. But they're also revealing aspects of the cosmos we didn't know about, pushing us to think harder, to be more creative, to consider possibilities we hadn't imagined. Perhaps 100 years from now, when we have a deeper understanding of galaxy formation in the early universe, when we've resolved the tensions JWST has revealed, astronomers will look back on this era as a crucial turning point. They'll see that JWST didn't just confirm what we thought we knew. It challenged us to know better, to understand more deeply, to construct more accurate models of cosmic history. 8 billion years old, humans have been studying it scientifically for a few centuries. We've made remarkable progress in that brief time, but we're still in the early stages of understanding. We've barely begun to comprehend the full story of how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. Every observation adds to our understanding. Every puzzle pushes us to think harder. Every contradiction between theory and data is an opportunity for discovery. JWST, with its stunning observations of the early universe, is giving us many such opportunities. The massive galaxies existing at Z10, Z12, Z13, and beyond, they're not just data points, not just problems to be solved. They're messages from the distant past, from a time when the universe was young and different and filled with processes we're only beginning to understand. They're evidence that the cosmos is richer, more surprising, more interesting than our theories had captured. And isn't that exactly what we should want from our explorations of the universe? Not confirmation of what we already think we know, but revelation of what we don't. Not validation of our models, but challenges that force us to build better ones. The early universe, it turns out, was precocious. Galaxies formed faster, grew bigger, assembled their stars more quickly than we expected. The cosmic dawn was brighter, more vigorous, more dramatic than our models predicted. The first few 100 million years were a crucial epoch, a time when much of what would become the visible universe was already taking shape. We're privileged to be living in the era when humanity can observe this epoch directly, when we have the technology to build telescopes powerful enough to see back to cosmic dawn, when we can test our theories against observations of the universe as it actually was in its youth. JWST has shown us that the universe's childhood was fascinating, complex, and full of activity we hadn't fully anticipated. That's not a crisis, it's an invitation to understand more, to probe deeper, to refine our theories and expand our knowledge. The universe is speaking to us through the light of distant galaxies. JWST is helping us listen. And what we're hearing is that the cosmos is stranger, richer, more surprising than we imagined. That's not something to fear or lament, it's something to celebrate. Because a universe that surprises us is a universe with secrets still to reveal, with mysteries still to solve, with discoveries still to be made. And that means the adventure of cosmic exploration is far from over. In many ways, with JWST's observations of the early universe challenging our models and revealing unexpected phenomena, it's just beginning. The story of the universe is still being written. We're learning to read its earliest chapters, and those chapters are turning out to be more interesting than we expected. That's a beautiful thing, a reminder that reality is richer than theory, that observation trumps expectation, that the cosmos is endlessly capable of surprising us if we have the courage to look deeply enough. JWST looked, and what it saw was a universe more complex, more active, more fascinating in its early years than we had imagined. The telescope revealed that our understanding was incomplete, and in doing so, it gave us the greatest gift science can offer, the opportunity to learn something new about the universe we inhabit. The early universe was not what we expected, but it was real, and now we have the privilege of trying to understand it.